In this video, we're going to discuss how to pick information off of sinusoids that have been modulated, a process called demodulation. The key issue that we're trying to solve with demodulation is that our modulated sinusoid is at a high frequency, which makes amplifying and measuring it difficult. We already know that mixers allow us to translate the frequency of a signal, so can't we just mix high frequency signals down to low frequencies and call this finished? Unfortunately, no. That's because we depend on the local oscillator being in phase with our incident signal in order to mix the incident signal to baseband. I've shown an example of that not happening correctly on this slide. In this picture, a signal was mixed up to RF using a cosine, and we're using a sine wave to demodulate it. This results in a positive and a negative copy of the signal landing on top of each other at baseband and canceling completely. So we can only use a mixer to convert incoming signals to baseband if we know something about the phase of the incoming signal. As a result, we refer to demodulating signals using a mixer as synchronous demodulation, because of the need to be lined up with the incoming signal. IQ demodulation, which is pictured on the right of this slide, is also synchronous. If the local oscillator is out of phase with the incoming signal, then some of the incident signal's I value will wind up on the Q path, and some of the Q value will wind up on the I path. And as an aside, this results in the IQ constellation rotating, and the ability to analyze IQ imbalances by looking at graphical behavior on constellation is a nice plus of IQ representations. Also, as an aside, this block on the left of the IQ modulator is a power splitter. Recovering the correct phase to use in a synchronous demodulation is a really involved problem that involves a specialized feedback loop called a phase-locked loop. Phase-locked loops are used to align phase like this, are often called clock and data recovery circuits, or CDRs. Synchronous demodulation provide very good performance, but it's also possible to demodulate some signals asynchronously, which can reduce design complexity. Amplitude modulated signals are particularly amenable to asynchronous demodulation, which is one of the reasons they were so popular in early radios. Envelope detectors explicitly pick the amplitude off of high frequency sine waves. The presence of a modulated signal is also useful when designing an envelope detector because it gives us some bounds on the time constant of our RC filter. We need the RC filter to be slow enough that it filters out the carrier frequency, but fast enough that it can respond to the modulation signal. An example of an envelope detector operating on an amplitude modulated signal appears below the circuit. The dashed line is the output of the envelope detector, and you can see that it tracks the height of the amplitude modulated signal, but that there's a time constant when it is decreasing because the increase in our envelope detector is governed by the very fast diode response, but the decrease is controlled by the discharge of the RC circuit. It's also possible to use second-order harmonic distortion to mix a signal back down to DC, as pictured on the right of this slide. The second-order harmonic distortion has a DC component, and that DC component will vary as amplitude increases and decreases. This type of demodulation has a few issues. It relies on big signals and it's nonlinear. But it's easy to implement, and anytime that you mix a signal, Anytime that you mix a signal with itself, it's called a homodyne measurement, so this type of demodulator can also be called a diode homodyne. Asynchronously demodulating frequency modulation is harder than amplitude modulation, but it's still doable. One way to demodulate frequency modulated signals is to put them into a filter that has a sharp frequency response. The different frequencies in your input signal will have different amplitudes at the output because of the slope of the filter, which converts frequency modulation into easier to measure amplitude modulation. This type of measurement is called a slope detector. Various specific implementations of this exist, including one version that uses a center-tapped inductor and a differential voltage signals called a Foster-Seeley detector, and that's popular. Another option is using digital circuits to measure frequency directly. The frequency counter circuit in the middle of this slide uses a comparator to convert the input signal into a digital signal, and then that digital signal is used to clock a flip-flop. The flip-flop is configured as an accumulator, so every clock stroke will increase the count signal by 1. By looking at the rate of change of the count signal, the digital system can extract the frequency of the input signal. However, this relies on very fast digital logic, which is a limitation of the technique. Finally, one common piece of advice when modulating FM is just to take the derivative of the signal. Doing so results in the frequency modulating signal appearing as a coefficient of the sinusoid. However, building a fast analog differentiator is quite difficult, so this demodulation technique is more often used in digital signal processing once the signal's been sampled. Demodulating phase asynchronously is impossible because phase is always measured relative to some kind of time reference. However, it's possible to build circuits that detect the phase difference between a signal and a reference. A simple XOR does the job reasonably well, as shown on this slide. When the sign of the input signal is different than the sign of the reference clock, the XOR will be high, which means that the average voltage at the output of the XOR will be proportional to the phase difference between Vin and the reference clock. If you wanted to provide the reference clock yourself, then you could use a phase detector and a phase-to-voltage converter with some filtering properties called a charge pump in order to wrap a feedback loop around a voltage-controlled oscillator. This will align the VCO with the input clock, and the control effort applied to the VCO can be used to extract changes in the input phase. This type of feedback loop is called a phase-locked loop, and we mentioned how important they are earlier in this video. There are lots and lots of other things we could say about phase-lock loops, but we are not going to right now. So in summary, synchronous demodulation or downmixing needs clocks that are in phase with the received data, and making those clocks is challenging. Amplitude modulation is relatively easy to demodulate asynchronously using an envelope detector or self-mixing. Frequency modulation is harder to demodulate asynchronously, requiring a slope detector or a counter. And demodulating phase modulation requires a reference clock, so we often make PLLs for that.